Hello again, guys. We're back for 6.4 talking about scatter plots and trend lines. In Math 8, you talked about scatter plots and their correlation, so this should be some review. When we look at data placed on a scatter plot, we always compare our XY variables and how they're changing in regards to each other. So if they're both increasing, we say that this is a positive correlation. If they're both decreasing together, we say this is a negative, or sorry, if as the X increases, the Y increases, it's positive. But if as the X increases, the Y decreases, this is a negative correlation. And then if the data is just kind of random, it has no correlation. So work through the first problem on Pearson and then come back when you're ready for the got it. Go ahead, try it on your own, and then come back if you need any help or to check your answer. So it makes sense to set up a graph that is going to have the x-axis be the dollars spent, because as the dollars spent goes up, we'll be able to see how our gallons bought goes up. And when you graph the data, you see that, of course, as you spend more money, you will get more gasoline. So we call this a positive correlation since they both go up together. And then we talk about B. We consider the population of a city and the number of letters in the city name. So since we're talking about letters in a city name compared to its population, try to decide to yourself what kind of correlation that would have. Of course, we know that the population in a city is not relative to its name. We can find lots of instances of that, but it just makes no sense. For extra practice, go ahead and try numbers 1 and 2 on your own. Pause the video, come back after you graph them, and decide what type of correlation the graph has. So when we're tracking the sale of jeans, as the average price goes up, the number sold goes down, probably because people are not willing to pay as much for jeans. So when it's cheaper, the price goes up, or the amount sold goes up. And gasoline purchases, as dollars spent goes up, you of course get more gallons. So that's positive correlation compared to our negative correlation up here. Alright, so depending on what you expose yourself to, TV, movies, that sort of thing, you may have heard people talk about extrapolating data. So what it means to extrapolate data comes from looking at our trend line. So as you saw in the last two problems, I showed you a trend line based on our data. So a trend line is a line drawn through to try to hit as many points as possible, or take the trend of the points, and it will show the correlation. So when there is no correlation, we cannot really draw a trend line. So interpolation is estimating a value between other known points. So if we were going to estimate something inside of here, that would be interpolation. And extrapolation is outside of the point. So if we say, okay, so as x goes up, y is going up, so we could continue to extrapolate and say my x values out here would probably have a higher y value. Work through problem 2 until you get to the got it, and then come back if you need help or to check your answer. What we want to do down below here is make a scatter plot and then talk about what is the approximate body length of a 7-month-old panda. So that will either be interpolation or extrapolation. Because I see 7 months is going to fall between data that I have, it's going to be interpolation. So go ahead, make that scatter plot and try to interpolate what you think the body length would be. So one of the good things about creating a trend line for the data is then we can create an equation. So you'll see that my graph here, once we put all the points on and have a trend line, I can see where the y-intercept is and I can figure out the slope. So we can go ahead and say that this would be the equation of this line. And when I plug in 7 months, well, x is my months, my independent variable. So I can plug 7 in for there, and we get about 24.4 inches for our answer there. Now we look at B, we want to talk about, do we think we can use this same model, this same equation to model for an adult panda or a 3-year-old panda? So take a moment and think about that. And of course, if you think about humans or most other animals, adults don't grow at the same rate as babies or children, so we cannot use that same model. The model would have to change, our equation would change. So here in practice problem 3, you've got 4 parts you want to try and do. You want to make a scatter plot of the data pairs, then draw your trend line through the data pairs, then write the equation, and then try to estimate the attendance in 2005. So that tells you that you want your x-axis to be the year of attendance. So here's what I did for my data here. You can see I broke my graph so that I could more easily show the values and just start right at 250. And of course that's the attendance in millions. So then I draw my trend line here. The equation that we get is right around y equaling 5x minus 9,690. And then when we plug in an x for that, we could say that our estimated value is 335 million. Now you may have predicted just slightly less than that, because if we look here at where 2005 would be, you could guesstimate it'd be a little bit lower. If you look here where 2005 falls, you'd assume it might be between there. But of course, that's exactly why we're just trying to make a prediction. So now for number 4, go ahead and try to make a data plot using the same pair, or sorry, not the same, but years and then revenue. So instead of using years and attendance, use years and revenue. Then we want to predict the revenue in 2012. So that's going to be a much further prediction. That's going to be an extrapolation, as opposed to here was an interpolation. So you see here we have all of our data points placed. We have our line drawn, and from that line we can say the equation is right around y equals 0.33x minus 650.75, because this is in billions. So then we can say about 13.2 billion once I plug in 2012 for the year. Now you might be confused about where we've gotten these y-intercepts. I realize I should stop for a second and explain that in case you have any issues. We're not at our y-axis. We are nowhere close, because if we were at year 0, I really doubt there would be people at our theme parks. So that's why we have to choose a couple xy pairs in here to find out what that y-intercept would be. So anytime our line of best fit has a slope of 1 or -1, we call that a strong correlation. A +1 slope would be a strong positive correlation, and a -1 slope, of course you can guess, is a strong negative correlation. So go ahead and work through problem 3 in the Pearson module. You're going to need to have seen problem 3 to deal with part B here in the Got It, and then try the Got It. Come back when you want to verify your answer. So one thing that's convenient to do in a situation like this is if we make this year 0, especially since it uses 2000, it's nice and convenient. So you can make that your x value of 0 to figure out what the cost is relative to the year. And as you see, the cost will continue to increase each year. So you want to find your slope by finding the change in y, the change in your cost, relative to the academic year. So once we work that out using the same method as in problem 3, we find our prediction to be about $9,964. And of course, the 2016-17 school year is going to be upon us very soon. You guys won't be in college till after that. And then if you look back at problem 3, the slope tells us that we know tuition increases, or sorry, it wasn't tuition in problem 3, but that it changes about $409 per year. I'm not going to worry too much about number 5 right now. We're going to do more with graphing calculators when you get into Math 2 in high school. I actually put up a link to an emulator that you can download if you'd like. But we plug in this data to our calculator, and it spits us out a nice function that then lets me predict. And based off that function, we can predict about 1,542 million tickets. So of course that's in the billions now, 1.5 billion. Go ahead and check out this Got It, though, if you've made it here in the Pearson lesson. Determine if you think there will be a correlation, and if so, explain whether you think it will be a causal relationship. So when we think about these, we talk about the cost of a family's vacation and the size of their house, like the house they live in, not their vacation house. So when you look at it like that, of course, their vacation could be really expensive, but the house they own back home may not be that large. So we say there may be a positive correlation, but it would not be causal, because that wouldn't actually relate. Now in B, we talk about time spent exercising and number of calories burned. Of course, if you spend more time exercising, you're going to burn more calories. So we say there is a positive correlation and it's causal. All right, when we look at problem 6 and 7 here, pause the video and try to determine on your own if you think there's a relationship and if it's causal. We see the amount of time that we would study for a test and the score that we receive. Well, if I study for more time, I would assume I would receive a higher score, so that would be a likely positive correlation, and it would be causal because the time you spent studying causes your higher score. Now we look at a person's height and the number of letters in that person's name. Well, we know that names are given way before we know how tall you're going to be, so there is no correlation and it would not be causal. There's no relationship there whatsoever. So like I said, we haven't done much with graphing calculators this year. I did not require you to have one. In Math 2, you're going to do a whole lot more of this. So when we look at this got it, and we would plug these values into a graphing calculator to see what this would tell us the trend was going to be, or we can just plot it on a graph ourselves. But if we do that, we see the graph that we get is going to look something like this, and that would actually be starting to model an exponential curve, because we know the value of a car most normally never goes to zero. It drops quite dramatically in the first amount of time you own it, but then the decrease in value starts to slow down. The longer you own it, it does not keep losing as much value. So older cars will sometimes hold their value, and certain car types hold their value better than others. So I'm not going to require you guys to do 8 or 9 because I know not all of you have a graphing calculator, but if you do, and if you've plugged it in using the method explained on Pearson, you would end up with a graph looking something like this. You'd see that it's exponential, and here would be our predicted value of right about $60.52. And then in number 9, also looking at a bacteria culture, we know a lot about bacteria, and it gets really interesting as we study it over time. We see with this bacteria, and actually as we start to talk about things, certain things have half-lives, and we'll get into that in Math 2 also. We see the amount of bacteria drops quickly, and then it slows down, slows down, slows down. It may never actually go away. There may always be a certain amount of bacteria able to be found. So that's all I have for 6.4, talking about scatter plots and trend lines. So please let me know if you're having any issues, guys. Again, I will not require you on the final to do the graphing in the calculator. So aside from that, just make sure you do your practice work and get ready for the test in class. Thanks. Have a great day.